The light is on. I'm a prisoner to a light, you know.
Computers ruin our lives.
Yeah. All right. So we're going to go back and summarize a little bit on what we were discussing about information theory, and hopefully we can start moving to some things related with Bayesian inference and homework 1. So let me. This is a huge subject, right? And everybody who works with data science and Bayesian inference needs to know about information theory. And really the best reference that links the two topics is this book by David Mackay. The book is free, actually. You can download it from the website. And it has, I believe, like 20 video lectures on information theory that you can just, when you have nothing else to do, those would be nice lectures to hear. I mentioned this many times, right, and people make fun. There is no excuse these days. Sorry, I did not know about this. Why? Because anything you want to know, it's there. Okay? The old days, you had to go in the library and keep digging, and it's like, good luck. Unfortunately, now you guys have everything there. So the task is enormous. Okay. So let me go rapidly on some of the things we discussed. So we first introduce this concept of the information that we learn, or the degree of surprise when we see a realization of a variable, and we call that age of x. Okay, we said if we observe two events that they are not, they are unrelated, independent sort of, then the degree of surprise of the information we learn when we observe x and y is obviously the information observing x and y. We related this with the independence relation in probability space, and then we said an obvious definition of h will be minus log of p of x. Okay? And when you average this, and you're interested on the average information to transmit x, okay, then you come up with a definition of the entropy of a random variable. Okay? And so this is written here for discrete random variables, but you know, the same thing will be true for continuums. You substitute the summation with an integral of p log of p. Okay. I gave you one little example that you should study, and I think one of the things we try to emphasize is that if you have words that appear with high probability, you need short codes to represent them. If you have something that is very rare, you need longer words. Okay? And we stated Shanon's theorem. I don't know why I put it on the bottom, because it's a very fundamental theorem that basically the entropy is a lower bound on the number of bits that you need to transmit the state of a random variable. Okay? All right, more definitions. I think I went very fast on this, but since there was nobody with statistical mechanics background, I mentioned people in physics, they like to have their own way of introducing entropy. So effectively here we have n objects, and we try to arrange them in a number of bins. Ni is the number of objects we put in bin I. So Ni factorial is the number of what the physics call microstates, how many microstates I can have on each bin, so how many different arrangements, and then effectively the total number of different configurations you can get for all possible arrangements of these objects on the different bins is like that. And if you define the entropy to be the log of this multiplicity divided by n, you can show with some approximations of these log factorials that this effectively gives you the same definition as Shannon's information theory, basically that the entropy is minus the summation of pi log of pi, For now, this pi are the occupation probabilities for the ith bin. So it's basically Ni divided by N. In many books in thermodynamics and things like that, you will see variations of these definitions. And the concept of entropy comes from multiple fields. It's not just in information sciences, it comes everywhere because things in life are all connected. All right. So we, I think I gave you this two pictures to convey the message here. If a distribution is sharp, like a delta function, so if something is deterministic, you're not learning anything new, so the entropy is small. If something is spread like a uniform distribution, the entropy is higher. And we proved, we didn't do the algebra because the algebra is actually one line, but we proved that if you look at the discrete distribution that takes, let's say, a given number of states, the discrete distribution with the maximum entropy is, which distribution? The uniform. All right, and remember, when you try to maximize entropy and everything else, we always have to normalize here, and so the summation of p of xi equal to 1. And the entropy, so if you plug in this inside the entropy definition, for a discrete variable with m states, the entropy is basically log of m. And I showed you a little trick on using Jensen's inequality, where you can prove that the entropy of any other discrete distribution is less or equal to log of m. Okay? And we will summarize again Jensen's inequality today. So let me see. Oh, I just added this thing on the update on the slides. We will see this. Basically, this is Jensen's inequality written in terms of logs directly. So the expectation of the log of x, all right, is less or equal to the log of the expectation of x. So in this case here, actually treat, when I write this equation and I say x, treat as any function of x, all right? So x here is 1 over p of xi, all right? So this is the expectation will be the probability times log of something. This is less or equal to the log of the expectation, there's probability, of x, which in this case is 1 over pxi. This cancel out, so you get m here, and there's log of m. Okay? This equation comes again in other slides, you know, if you miss it. Jensen's inequality, extremely, extremely important in statistics and machine learning. We gave an example of this binary entropy function. So if you have a binary variable, the entropy looks like that. This is very fundamental. So for example, you know, people that do classification problems, you know, is it 1 or it's 0? They do use loss functions based on this binary entropy, so it has lots of applications in multiple areas. It looks like that, and it's maximum in the middle symmetric. So this is the definition. I think that's where most probably we stop. This is the definition of the of the entropy for a continuous distribution minus p log of p dx. And I mentioned, we didn't do this, but I mentioned, be sure if you know the entropy of x and you want to calculate the entropy of some function of x, don't forget that probabilities transform as probabilities, not as functions. So don't, you know, so if you try to compute the entropy of y, all right, be sure that you account for the Jacobian of the transformation. All right, actually we did this slide as well. So for continuous distributions, we try to find out which distribution has the maximum entropy with the additional constraints that the mean and the variance are fixed. So if the mean is equal to mu and the variance is equal to sigma square, we asked what is the continuous distribution that is maximizing the entropy. So we have three constraints. normalization. This is the mean equal to mu, the variance equal to sigma squared. Remember, lambda 1, lambda 2, lambda 3, they're not penalty numbers, all right? If you think of optimization, they're Lagrange multipliers. So when you state a problem like that, the unknowns is not just p of x, but p of x, lambda 1, lambda 2, and lambda 3. So you have to take derivatives with respect to 4 arguments. And the only thing you need to be careful is how you take derivatives with respect to p. And how you do that is all on calculus of variations. Okay? If you know nothing about it, the idea is very simple. You have this equation written like that. Write a perturbation of this equation when p becomes p plus delta p, and subtract the two equations, and set the difference equal to 0. Okay? When you do that, eventually, and applying the constraints, you get the Gaussian. So the Gaussian is the distribution that has this, is as uncertain, if you like, in its predictions, with the constraints that the mean is fixed and the variance sigma squared than any other distribution. Okay? So it has, this has a lot of implications everywhere. And I give you here the exact result for the entropy of the Gaussian. This is for the univariate case and the multivariate as well. All right. I think we introduce. I don't know why I'm doing this. I think we did this already. So this is, so we introduced the KL divergence distance. So if we have, let's say the actual distribution is P, we want to approximate it with some nice distribution Q. The distance between P and Q is measured with what you see here. This is called the KL distance. And if you want to see basically how this thing comes from an information theoretic point of view, the idea here is when you try to transmit X through a channel, you build this channel using a code book based on the approximation Q of X rather than the exact distribution P of X. So effectively what the difference here gives you is if you use Q to approximate the coding, how much extra information will you need versus using the exact distribution. And that's the KL distance. Okay? From practical perspective, this is what you need to know. Okay? And it is important to remember that this distance is not symmetric. Okay? So when you reverse it and you have the distance of Q from P, it's a day and night. Okay? Complete different things come out from this. In some sense, some of the people don't like this distance just because of that reason that it's not symmetric, right? I mean, in nature, Euclidean distances, Mahalanobis distance, etc., they are all symmetric. This distance is not symmetric. So people use it because in many occasions it comes naturally, and because the algebra is also very good. All right? But there are new problems coming up now, lots of problems, where this distance basically will not work. Now, this term here, we call it the cross entropy. Okay? So effectively, it's the average information to transmit X when the code book is based on Q of X, this approximation, but the averaging is done with the exact distribution P of X. Okay, we emphasize that. All right, and I give you various results in the notes that you may decide sometimes in the future that you may need to use them. So if you have two Gaussians and you want to find the KL distance, you don't need to bother about the algebra, it's already done. It looks like that. If the distribution is, if both of them are multivariate Gaussians, don't need to bother because somebody has done this calculation for you. Okay? And then we went to Jensen's inequality. The Jensen's inequality is nothing else but an expression of the convexity of this function f. And I added this, I don't know if this was there on the previous slides, but I added or this diagram, effectively the definition of the fact that f is convex. So it says here, if I take lambda between 0 and 1, lambda times the value of the function at a plus 1 minus lambda times the function at the value b is greater than the value of the function at lambda times a plus 1 minus lambda times b. Okay? And in the notes, I give you actually the proof that if the function is convex, this is true. And also, if this is true, then the function is convex. Okay? Don't need to bother about the proofs, but just remember that this thing that we started to derive Jensen's inequality is for convex functions. So Jensen's inequality, it's applied to convex functions. If you don't have a convex function, but it's concave, take a minus sign and reverse the inequality. Okay? So we first extended this for discrete variables. If we said if the lambdas are the probabilities, the probability to get x equal to xi, and we effectively got this. Okay? You can generalize this to continuous variables. So f of the expectation of x is less than or equal the expectation of f of x. Okay? All right, and actually I edit this thing to show you in terms of the log. So if you want to apply f, you are going to apply for minus log. All right? So minus log of the expectation less or equal of v of minus log. So if you reverse it, the expectation of the log is less or equal to the log of the expectation. Again, you don't really need to remember all of these things because it takes 1 second. You say Jensen's inequality, wiki, and immediately on the top it will give you this. And you need to know when you have to play with logs, right, on using this inequality. And again, why do I really care about these things? Because effectively, you will never be able to calculate some quantities directly. So if you try to maximize, let's say, this thing on the left, you will not be able to do this. But if this is something easy, then you maximize the upper bound. And that's how this inequality comes. Okay, so I did one example, okay, that not useful from a statistics perspective, but basically I show you that this geometric mean is less or equal than the arithmetic mean of a number of xi's, okay? And simply we use Jensen's inequality for uniform distributions. Basically, we cooked up this example to show you that you can do anything you want with it, right? Okay. And a very trivial application of Jensen's inequality is basically to prove that this KL distance between P and the approximation Q is actually greater or equal to 0. And this is how this proof can be done with Jensen's inequality in one line. Okay? If you want to prove that this or this is greater or equal to 0, look what I have done. I move the log outside. This is greater or equal than P times Q over P. P and P cancel. Integral of Q is 1. It's normalized. So log of 1 is 0. Done. Right? If you think about it, the fact that somehow the log comes out and, you may think it's magic, but when later on, not in this course, but if you take another course with me and you learn about variational methods on approximating complex distributions with some easier to work with distributions, you will see this type of calculations being used effectively all the time. Okay, so the distance is greater than or equal to 0, and it's only 0 if P and Q are the same, which sort of, it's good, right? That's what you like on a distance between two distributions to be like. All right, so I think we already have shown this. The entropy of any discrete distribution is less than or equal to the log of the number of elements in the discrete distribution, right? So if you say I have a discrete distribution with m elements, then this is less than the log of m, okay? So this, I saw the cardinality of x, how many elements are in x, like that, okay? And you can actually show this result again using the KL distance. Look at this derivation. Right before we show it, I don't remember how, all right? But here I'm showing it using the KL distance. So I say, let's take U to be the uniform distribution. So if X is equal to 3, right? If I'm talking about discrete distributions with 3 elements, this is 1 over 3, 4 elements, 1 over 4, right? So this is the number of elements. So I make U to be this distribution, and I want to show that the entropy of any discrete distribution is less or equal than that. So let's see, what am I doing here? I took the definition of the KL distance. You remember the KL distance is minus the integral or summation of P times log of U over P. So this is the first term, this is the denominator. Do you agree that this term is minus the entropy of X by definition? Okay. Now, here I'm summing in X, but log of U does not depend on X. So this I can bring out of the summation, and then the summation of P of X is equal to 1, and there is the proof, another way using the KL divergence distance. Okay, I mean, you can prove this in 10 lines, but with the Jensen's inequality, you can show this in a straightforward manner. All right, so let me use the KL distance now for something else. You may not appreciate it yet because we haven't really talked a lot about the likelihood, right? You remember the likelihood, when you observe data, the likelihood is the probability of actually seeing the data coming from that given distribution, okay? I will do this formally actually maybe starting today, but let me, I'm gonna go to the next slide. Let me do the following, and again, it may not mean anything to you today, but maybe it will click. So let's say we have the actual distribution P, and we want to approximate it with some distribution K that is easy to work. And in particular, you know what I want to do is, I want to assume that I don't really know the distribution P, the actual one. I only have samples from it. And somewhere I mentioned, if you only have samples, then you approximate the distribution with, how do we call that approximate distribution in terms of delta functions? So if somebody gives you, here's one sample, another one, and you put lots of delta functions, in a previous lecture I wrote down how the distribution looks with these delta functions. Is summation of these delta functions with equal weight, and if I have n samples, the weights were 1 over n. Okay? So, let's assume that I don't really have the exact distribution. Right? I don't have it. What I have is a number of samples, n, from that distribution, so I can really compute this empirical distribution. Now, so P is not available, this empirical distribution is available. This is actually what we will call a Monte Carlo approximation of P. Let's say now that somehow you want to fit this to some distribution with a nice parametric form, let's say Gaussian. And you may want to say, what's the mean of the Gaussian, what's the variance of the Gaussian, right? So we want to approximate Q to P, but because P is not available, we're going to try to approximate Q to the empirical distribution. And the way we're going to do this is by minimizing the distance between the empirical distribution of X and Q. So I use the definition of the KL distance. Now you notice here, I want to, the unknown here is Q. I want to minimize with respect to Q. I want to find the best Q. So if, let's say, Q is Gaussian, you don't know the mean, you don't know the variance, you say, what's the mean, what's the variance, okay? So the first term, you notice this times the log on the denominator does not depend on Q, so it's constant, okay? And what you get is, you get minus the empirical distribution log of Q, but the empirical distribution is delta functions. So when you integrate each delta function with Q, what do you get? When you integrate A delta function with a function, what do you get? The
The
value evaluated at that location of the delta function. So what you get is log of Q computed at each of the samples. You see that visually at least? And you know what? What is this quantity? Can you give me some physical meaning of this? There is a summation of logs. If it was not a summation of logs, it would be product over n of Q for every xn for given parameters. How do we call that quantity?
Factorial?
No. Yeah, well, it is factorial, but how do you, so if you have a distribution Q, right, and you have the samples xn, the product of Q at each of the xn, given the parameters, how do we call that?
Likelihood?
Likelihood. That's the likelihood under the Q distribution. So here is what you get. Minimizing the KL distance of Q from the empirical distribution is the same, look at this minus sign, as maximizing the likelihood under Q. This is very important, and actually, if you read sort of papers in the recent literature, so lots of people don't like anymore talking about likelihood because they think this looks more elegant. And so you look at them and you say, where did they get this? Well, you know, they're the same thing. Okay? So again, you want to find some approximation to P using some family of distributions, let's say a Gaussian, with unknown parameters theta. Because you don't really know P, but you have samples, so you minimize the distance of the empirical distribution of P from, of X from Q. And it comes out that this minimization is the same as maximizing the log likelihood, which is the same as maximizing the likelihood. The likelihood under Q. Okay? And if Q is a Gaussian, we can do that. Yeah?
So we do that to get Q? Because
exactly. Exactly.
So in the future, we're going to, because we don't know P, maybe it's impossible to know P.
Yeah, so yes. So for example, if you really want to have, rather than having samples, right, you want to fit this to a Gaussian, all right? You say, I want to have a real Gaussian to fit my data. So there is a problem, all right? You find this, and you know, if you do this without knowing anything of this, right? You say, I'm going to approximate it with a Gaussian. I'm going to calculate the likelihood. I'm going to maximize it. There is the mean. There is, and I'm just now showing to you that actually, if you're going to do the obvious, it's really the same as minimizing the distance of the Gaussian from the empirical distribution of X. So I'm not telling you anything non-obvious. I'm just putting it formally in some mathematical sort of form. Okay? All right. Let's continue with more definitions so we can finish this. Okay? So I'm going to define the conditional entropy. Okay? So basically, this conditional entropy, as you can see in the formula, is the average information, average because of this distribution there, needed to specify y if I know x. Okay? So this is the average information needed to specify y when you know x. And that's why we call this conditional on x entropy. From the definition of entropy, actually, you can appreciate that this nice, obvious-looking result has to be correct, right? The average information that you need to specify x and y makes sense that it's the information that you need to specify y given x plus the information to specify x. Okay? If you don't really believe on the obvious, you can use the entropy of the joint distribution and then take this joint and write it as the conditional times the marginal. You plug in this thing there, all right, and you will get two terms because you have a log. One will give you this, one will give you that. Okay? So again, this is the entropy of the joint, the conditional entropy, and this is the marginal entropy of x. Now, don't read this slide. I want you, when you go home, to read it. Actually, since you're not going to read the slide, let me just concentrate on this definition. suppose that I discuss about discrete distributions, okay? So this is our definition of conditional entropy. And let's say that I tell you that this conditional entropy is 0. Can you tell me what meaning do you assign to that for a discrete distribution? So if somebody tells you that the entropy of you know, yi given xi or something is 0, or the entropy of y given x is 0, what does that mean for a deterministic, for discrete distributions? I don't hear. So remember, this is the information that you need to describe y given x, right? So if this is 0 for a discrete distribution, what does it mean?
Yeah, same.
It will be the same. But there are two different sort of random variables, right? I mean, I'm saying
So it's independent?
independent. Okay, we're converging, not really. So I specify y, and the extra information I need to specify y, I specify x, and the extra information that I need to specify y is 0. So what does it mean? That x brings no additional information.
Why does it
Equivalent.
bring? If you know x already,
Yes,
then y doesn't tell you anything else. Like it doesn't.
which
give you
means
surprise.
that y is a function of x.
Yeah.
So they're not independent, exactly the opposite. So y is a deterministic function of x.
So it means it means py comma x equals px.
A little bit yes, a little bit different actually than that, okay? So what it means here is, I don't want to write this in terms of conditional distributions and independence, right? Means, if you give me x, and this information to describe y is 0, y has to be a function of x, a deterministic function of x. Okay, so let's not bring this independence because we will get confused. No relation to independence, right? Means you specify x, all right? Then you have specified y because y is a function of x. So what the slide on the next slide does, it actually proves that for a discrete distribution, that's exactly the case. Okay, so it's good sort of to have that meaning, right? That what this conditional entropy means. All right. You remember when we discussed about independence, and independence is a strong relation. It's written in probability space. Independence implies uncorrelated variables. And so let's bring a rigorous way to define independence using KL distance. So this is called mutual information. Okay, you will see this actually everywhere in papers in the literature because a reviewer will ask you to compute this. So mutual information is really the KL distance between the joint probability of x and y and p of x times p of y. You remember the independence? Independence means this equal to that. Okay? So if I want to see if this is equal to that, a good distance measure is the KL distance between p of x and y and p of x times p of y. And this is what we call mutual information. And obviously this is 0 if x and y are independent. Okay? So I haven't really said anything new here. What is new is that a good way to express that this is equal to that is basically to express it through this KL distance, and we give it a nice name and we call it mutual information. Okay? Mutual information defines independence of, okay? So if you rewrite, so if you take, let's say, one of the marginals, like p of x, and you take the joint p of x and y together, then you get the conditional p of y given x. And if you split this in the log on the numerator and minus the log of the denominator, what you get is, you get that the mutual information of x and y is the entropy of y minus the conditional entropy of y given x. And actually, that's another way to now look at independence. You remember, this is the extra information needed to describe y given x, right? And this is the average information needed to describe y with no reference to any x's. Obviously, if these two things are the same, I equal to 0 and the x and y are independent. Okay? So I think there is a graph that I can, I extracted from one of the books. I mean, this shows this independence relations in terms of set theory in our schematics. So don't, don't use this, I mean, use this with some common sense what the equations imply here. So obviously, this, let's say, big circle here is h of x, and h of x is written as a of x given y, and the mutual information. Similarly here, h of y is given the mutual information plus h of y given of x. So this is symmetric, sort of the two equations are the same as is there. One way to actually see this in a Bayesian setting, and we may come back to it, is as follows. Think of x and p of x being your prior distribution and y being your data. So when you look at this distance, it's like asking how close is my prior to the posterior? How much extra information do I bring from the data, right, beyond what I had in the prior? Okay, so that's sort of the type of meaning you want to assign this. But again, I haven't said anything about priors and posteriors, so this is just, I'm throwing it there on the air. Okay, so again, this is this mutual information. This is this from the definition of the conditional entropy. So effectively, you can actually put the two things together, and you can show that the entropy of x and y is less or equal to the entropy of x and y. And this is equal to 0 when this is 0, and the mutual information is 0 when x and y are independent. You can actually prove that this is necessary and sufficient condition. So if the variables are independent, this, you get an equality here. If you get an equality here, you can prove that the variables are independent. I'm applying this, I'm not going to do this example. I'm applying this type of calculations for the mutual information for the Gaussian. So, I have all the analytical results so you guys can look at. All right, let me finish with something, and I'm going to be sort of very abstract, no details or anything. Lots of people think that, especially for distributions defined through data, right? For distributions that basically you need to fit them, you need to fit data using kernel estimation. The idea of mutual information is a little bit on the air, because the mutual information as a KL distance is an integral. How do you compute that? I mean, if I have a discrete distribution defined in a histogram, how do I go and I compute this KL distance, right? Because, again, I haven't said anything about when you have histograms, how you compute distribution. But for those who have done this in practice, if I change the size of the bins, the answer can be completely different, right? Or how many bins I use and all of these things. So the last, I think, 5 years or so, people started to address this problem because they realized that they declare variables independent when actually they are not independent. Okay, they are strong nonlinearities, and I saw you. I think you remember I had there was a picture that I showed you with things where the correlation coefficients were 0, but the x and y were highly nonlinearly related. So people define what is called a pointwise mutual information, which is really this minus the log of p of x, p of y, p of x and y. You remember this is the log that appears inside the definition of the mutual information, the KL distance. So the mutual information, what actually was, it was the average of this with respect to P of X and Y, okay? But the idea here is this is point-wise mutual information. So if you binarize, right, if you split in little bins the distribution, you can calculate this locally for events. All right, locally for events, not, you don't have to compute an integral. Okay, so if you want to find the mutual information, you can start with this, defined locally, and then you can average with this distribution, and somehow you can come up with I. So let me show you what this maximal information coefficient is, okay, in a very abstract way, okay. So what you do is, so let's say you have this variables X and Y. You basically try to do something similar to kernel estimation. You split the domain in two-dimensional grids of size X and Y. Right? If you imagine you have lots of samples here and there, etc. So you put a lots of bins, and the grid that you use is X times Y. Okay? Now, even for a grid of size X times Y, you can fit a lot of different partitions. Maybe, the bin here is very small, there is bigger, lots of different variations, okay? So I define this coefficient M for a given partition X times Y, all right, as the maximum of the mutual information of X and Y defined on that grid G, defined by the log of the minimum of X and Y. Okay, and then what I do is, to define this maximal information coefficient, I further maximize this for all possibles X and Y that they are less some upper bound number. So you can think, you say, you know what, I'm going to use, if this is, let's say, the variables are on the scalar random variables, you can say I'm going to use X and Y less than, I don't know, 1,000. Okay, so if you maximize that, you come up with what is called maximal information coefficient. It's complicated. There is a paper, and actually there is software. This paper was published in Science. So obviously there was lots of science to it. Okay, and because it changes the way we look at things, and I'm going to show you some results. The only thing you need to remember is it's sort of defining a mutual information, but you try to maximize overall partitions, all different grids where you can do your calculations. That's all. Okay, that's all I want you to know. So let's see what the particular data set that was reported on this paper. So this the data set they considered. And I don't remember if it was in biology, but it was something in or ecology or something like that. But there were 357 variables. No, actually not biology here. So I see social economic indicators by the WHO organization, World Health Organization. So maybe it was something biology. All right. So what you see here is the correlation coefficient. Remember, the correlation coefficient is the covariant divided by the standard deviations, and this is this maximum. How do we call it? Maximal information coefficient. Okay, so it has different points that you see here: C, D, E, F, G, H, etc. So let's look at some points. Point C has very small correlation coefficient. This is the 0, and also has very small mixed score. Okay, so if you actually, so obviously this indicates from the correlation coefficient that maybe these variables are uncorrelated. The MIC is also very small. So if you actually plot certain relation of two of those variables, you can see they're all over the space. So really they're not correlated. Okay, so that's point C good. Okay, that's so small correlation, small mix seem to agree. So if you look at point D, the correlation coefficient now is very big, okay, and the MIC coefficient is very big. So if actually you take two variables and you plot them together, you see the correlation basically is linear. Okay? So highly correlated, and you remember the correlation coefficient captures linear correlations. Linear. All right. So let's go and look at points F, for example. So we can just do one of those. F has very small correlation coefficient, so immediately you say uncorrelated, but has very large mixed score. So if you look at F, this is how the data look like. They're non-linearly related, okay? So the correlation coefficient basically fails to capture this. The mixed score basically captures that. And there are more curves like that on the paper. And somewhere actually on that, on a review of this paper, it stated, somebody, you know, I don't, hopefully not the authors, that this is the mutual information for the 21st century. Basically, that this is the way we're going to be trying to figure out independence between high-dimensional variables using this mixed score. And I believe if you search on the web, you may be able actually to find the software on this, so you can use it in your own work. When do we finish? Remind me. 20? Really? It's too bad. You guys are going to have to do all the homework on your own.
Yeah.
All right. So, the homework is not due until next week. And you notice I gave you, I cut and pasted the slides, so you can only read, I don't know, 50 slides. They're not actually all very dense. You don't need everything there, but they contain all the information for all the homework problems. Okay. So. I'm going to cover these topics on Tuesday, but let me just go very fast and tell you what we're going to do. We're going to formally introduce maximum likelihood. All right, so we're going to do this formally. I am going to apply maximum likelihood for the univariate Gaussian. So if you have a Gaussian, you have a bunch of data, you know, how does the likelihood looks like, and what is the maximum MLE estimate for the mean and the variance. We're going to do this for the univariate Gaussian. I think that's your homework problem. Problem 1, I believe. And also we're going to do this for the multivariate Gaussian. Something easy to read. We already have seen Bayes' rule, but now we're going to extend it in the context of Bayesian statistics and introduce formally the concept of a prior, likelihood, and posterior. Okay? So obviously the prior, you know, you try to estimate some parameters. You have some distribution that gives you the likelihood, you have some prior for the parameters. The product of the two will give you the posterior. All right? And the posterior actually, if you want to do point estimates the way we do with the maximum likelihood estimate, you can do that, and you can find the map estimate of the parameters. The maximum a posteriori estimate basically for the parameters effectively would be sort of like a regularized MLE. It would be MLE, but it would be more stable to something that will work if you have very few data or very noisy data. So something that is better than MLE, so we will see that. Of course, the fact that we have the whole posterior, that's way much more information, okay? So this is what we're interested in. And we will discuss what's called the predictive distribution. So if you collect data today and you want to predict what the temperature will be tomorrow, can you actually do that? And the predictive distribution will allow you to do that. And then the rest of the slides, you know, contain a lot. I was hoping to do this part today, actually, so I don't have the rest of the topics. The rest of the slides contain a lot of examples. For example, the example I was going to do today is a univariate Gaussian with a known mean. So what I was intending to do is put some prior on this mean, then get a posterior for that mean, and do a lot of different type of calculations. Okay? So the slides, you can actually read them, I trust, so you can start working on the problem. I'm going to go back to the office, have a quick lunch. So if anybody has questions about the homework or anything about the lectures, I'm going to be there from 1 to 2 o'clock. The TAs told me they're going to devote 2 hours on Monday to go through the homework problem, okay? Any questions you have, you can even email them. And if they send you a solution, don't tell me about it, okay? So office hours today, read the slides. If there is something missing that needs explanation, email me, and I will either modify the slide or email you back, okay? All right, so I'll see you back on Tuesday.
Where is your office?
My office is at 311 Cushing Hall, which is the other side of Fitzpatrick. Okay, 311I. I am worried that I had the microphone off the whole lecture. What? It was on? It was on?
Yes.
Okay. It was on? The microphone?
Yes.
Huh? Okay. It was on.
Oh, maybe not, but it works. It was very
No, but if it is not on, then we have problems.